Welcome back, students. In this video segment, we will look at one very, very important subject or section for the mathematics of the sciences called the Fundamental Theorem for line integrals. The Fundamental Theorem for line integrals. Before we get to the actual Fundamental Theorem, we need to talk about something extremely important in physics and in more generally for the mathematics of the sciences called conservative vector fields. Conservative vector fields. So let's take a look at a definition. Let's say we start with a vector field f of x, y, z. So let f of x, y, z be a vector field. Okay, so we say that f of x, y, z, or f, is conservative if we can find a scalar function, not a vector function, but a scalar function. Let's say f of x, y, z, such that our vector field f is the gradient of that scalar field. Right now this may seem very strange, but to a student of calculus-based physics, this idea of having a scalar vector field is enormously important. Okay, the function f of x, y, z is called a potential function. So f of x, y, z is called a potential function. If you've had calculus-based physics, and I think a lot of you have, the idea of a potential function is very closely related to the idea of potential energy, extremely close. So that topic will come up toward the end of the lecture, the concept of potential energy when we look at the work energy theorem and conservation of energy as our last idea. Right now we want to concentrate on conservative vector fields. So let's take a look at a specific example. Okay, so example. Let's let f, in this case, f of x, y. The concept of a conservative vector field doesn't have to be in 3 space. It can be in 2 space. So let's say let f of x, y equal 2xi plus 4yj. So we're looking at a vector field, and I want to know if f is conservative. So is f conservative? Okay, that is, can we find a scalar function such that the vector field f is the gradient of that scalar function? So that is, let me write that out. That is there a function, an f of xy, let's do that way, and f of xy such that my vector function is the gradient of that scalar function, f of xy? Well, the answer is yes. Answer is yes. We're going to spend some quality time figuring out how to determine whether it's yes or no and how to construct that potential function. But right now, let's just take a look at the solution, a solution. So let f of xy equal x squared plus 2y squared. X squared plus 2y squared. Okay, so let's check it. In order for the vector field f of xy to be conservative, the gradient of this mysterious scalar function that I found needs to equal the vector field. Okay, so let's see. The partial of f with respect to x is 2x, and the partial of f with respect to y is 4y. So capital F, the scalar field, or the vector field rather, equals the gradient of small f. Okay, and that's what makes a conservative field a conservative field. If we can find a scalar function, so basically when you take its derivative, not quite its derivative, the gradient is a vector field. So when you take the derivative, you get the original vector field. Again, not literally the derivative, because the gradient is a vector quantity. So we're gonna push forward by answering 3 big questions, okay, in full detail. So here are some big questions, some really, really important big questions. First, how do we determine whether we have a conservative field? How do we determine that without actually looking for that scalar function f? 2, once we've determined through some sort of test or whatever how that our scalar function, our vector field is conservative, how do we find the potential function? How do we find the potential for a potential function? And 3, which I think is probably one of the most important questions to answer, is what are the physical consequences? And by the physical consequences, I don't mean the only ones. What are some really important physical consequences of having conservative vector fields? Okay, so in order to address these 3 questions, we're going to look back at a little bit of what we did in section 16.1. In section 16.1, we looked at vector fields. And I tried to give you several really important or really meaningful examples of vector fields. And one of them had to do with Newton's law of gravitation. And in constructing Newton's law of gravitation, we considered 2 masses, and we can consider those 2 masses to be a big mass of maybe being the Earth or the Sun, and the small mass as being the Earth or the Moon. So if we say let's let the big mass be the Earth and the small mass be the Moon, just for example, we noted that the magnitude of the force is experimentally determined, and actually not just experimentally determined, but analytically determined by Newton and Kepler to be the magnitude of the force. The magnitude of the force is equal to the product of 3 constants. So G times M times big M times small m, a constant over the distance between the centers of the 2 objects, the centers of the Earth and the center of the Moon. Okay, then we further constructed the actual force by looking at, let's say, calling the position of the Moon XYZ, or the location of the Moon is XYZ, if we put the center or the origin in 3 space at the center of the Earth. And we constructed a unit vector pointing from the center of the Moon to the center of the Earth. This is all stuff we did in 6.1. I just kind of like to review it a little bit. We considered the vector, position vector x, and remember we're allowed to use x as a position vector, not just our usual r for position vectors. We said let x equal the position vector whose components are x, y, and z. Okay, then we constructed a unit vector pointing directly from the center of the Moon back to the center of the Earth by taking the opposite of x. Remember, the position vector points from the origin to the center of the Moon, so a vector pointing directly back would be the opposite of x. And we turn that into a unit vector by dividing by its magnitude. or more precisely, I guess, multiplying by the reciprocal of its magnitude. So that gave us a unit vector. Then we constructed the actual Newton's law of gravitation, the actual force vector, force, evaluated at the position vector x, to equal the magnitude of the force times the unit vector pointing backwards from the center of the moon or the center of the other object to the center of the bigger object. In this case, we're looking at moon and Earth. So that gave us g, the universal gravitational constant, big mass times small mass, over, and the distance r between the two centers is nothing more than the length of the position vector. So r squared will be the length of the position vector squared. And the unit vector is negative x, vector x over length of x. Okay, again, we did all this in section 6.1, but I wanted you to see it again because we're going to kind of move forward from this formula that we looked at to the concept of a conservative vector field. And if we multiply all this stuff out, or simplify maybe a little bit, we get negative g big M small m over the magnitude of the position vector cubed times the position vector x. Okay, now what I'd like to do is determine whether this function is this vector field is conservative. If you've had some physics, not even calculus-based physics, but even non-calculus-based physics, you know the answer ahead of time. But for those who don't, let's see if this is a conservative vector field. So we're going to keep moving forward with this formula. I would like to write this vector field component-wise. Okay, so what I'm going to do is I'm going to replace the x, the position vector, with the components x, y, z. Okay, and the length of the position vector with the square root of x squared plus y squared plus z squared. So if you missed that, I'm going to write this as x, y, z for x, and the length of x is the square root. I'm going to need more room here. Let me make us some more room. That's a little better. Okay, so the length of a position vector, or any vector, is the square root of the sum of the squares of the components, z squared, so that's the length of x, and then cubed. Okay, so let's move forward with this. Let's write this vector component-wise. Okay, so we can write this as, maybe factor out the constant negative g big M times small m times the vector whose components are x over x squared plus y squared plus z squared to the 3/2, square root cubed just to the 3/2 power. The other two components are going to be very similar. They're going to have the same denominators. The numerators are going to be y and z respectively. So we have plus or comma y over x squared plus y squared plus z squared to the 3/2, and our third component z over x squared plus y squared plus z squared to the 3/2. Now we haven't talked about how to determine ahead of time whether we have a conservative vector field. So what I'm going to do is I'm going to use sort of a shortened method that we're going to look at in about, I don't know, 10 or 15 minutes or so ago to construct a potential function. Okay, so what we need for this to be conservative is we need to find an f of xyz such that the gradient of that function is the vector field, so that the f is equal to the gradient of that scalar function. Remember, the gradient, though, is the vector whose components are the partial of f with respect to x, the partial of f with respect to y, the partial of f with respect to z. Okay, so if we need that vector field above, capital F, to equal the gradient of this vector, or the scalar function, we need the components of the vector field to equal, in order, the components of the gradient field. Okay, so we need, in particular, for the partial of f with respect to x to equal negative g big M small m x over x squared plus y squared plus z squared to the 3/2. And of course, and the other two equations with the partial of f with respect to y equaling the second component, and the partial of f with respect to z equaling the third component of my force, or my force function. Okay, so let's just concentrate on the first equation. Again, we're looking at an abridged, a sort of modified, shortened version of a method we're going to be using very soon to kind of construct a potential function. So, how am I going to go from the derivative with respect to x of a function to the actual function? And the answer is, you know the answer. If you know the derivative of a function, if we knew it, let's just look at a simpler example. If the derivative f prime of x was, let's say, 2x, then f of x would equal the integral, the antiderivative of 2x, the most general antiderivative of 2x, or x squared plus a constant. So we have a similar situation, except it's a partial derivative that we're given. So what we're going to do is we're going to integrate both sides of this partial derivative with respect to x to reconstruct the function. So it seems reasonable. That f of x, y, z should equal the integral of the partial derivative of f with respect to x, and then integrate that with respect to x. Okay. So let's do that. Let's see what we can do with that. Let's see if we can consider integrating the. In fact, we don't need to when we integrate this, we don't need to involve the negative g m big M times small m. So take a look at the derivative. I'm going to put in parentheses the constant negative g big M times small m. Let's just integrate that function without that constant. Okay, and then put the constant in the end when we construct the function. So we're looking at the integral of x over x squared plus y squared plus z squared to the 3/2 power with respect to x. Now, when we took the partial derivative with respect to x, that means we held y and z as constant. So it seems reasonable to assume that if we're going to go backwards and integrate with respect to x, that we should also hold y and z constant. So we're going to do that. When we integrate with respect to x, we're going to hold y and z constant. Okay, so when we do that, it's just a real simple u substitution. So I'm going to let u equal x squared plus the constant, holding constant y squared plus the holding constant z squared. Okay, we get du equals the derivative of x squared is 2x. Now we're holding y and z constant. So the derivative of y squared and z squared is 0. So du equals 2x dx. So that x dx equals 1/2 du. Never thought we could do this. I bet you never never thought we could integrate functions of more than one variable. Okay, sure. Okay, so let's continue on. This becomes, let's see, du, 1/2 du is x dx. So this becomes 1/2 the integral of 1 over u to the 3/2, or u to the negative 3/2. Ooh, yeah. Clean that up. Du. And that gives us 1/2. Add 1 to the exponent, so negative 3/2 plus 2/2 is negative 1/2, so you get negative 1/2 over negative 1/2 plus a constant, or negative u to the negative 1/2 plus a constant. Okay, now we're looking for a single potential function. We're looking for one potential function. We're constructing, when we do this antiderivative, a whole bunch of potential functions. So I'm going to let c equal 0, because I'm only looking for a function, a single function, whose gradient is the vector field. Okay, and I'm going to do that right here. I'm going to let c equal 0, because I'm only looking for one vector. I'm looking for one potential function. Okay, we're going to become much more rigorous about this. We're going to look at a much more standard way of reconstructing or constructing this potential function. The idea right now is I'd like you to see that we're looking at, and I guess I already let the cat out of the bag here, that we're looking at the the Newton's law of gravitation as being a conservative field. Okay, now notice I found that f of x, y, z, a potential function, not the potential function, there's many potential functions, but a potential function then is, remember we ignored the constant g, m, and m, so is g big M small m over, let's see, x squared plus y squared plus z squared plus z squared to the 1/2 power. Now, a couple of things here. One, it looks like maybe I lost a minus sign, and I didn't. When I integrated, I didn't take into account that we had reserved the constant negative g big M times small m, so those two negatives canceled. The second thing is, you notice I never even considered the other two components, the partial with respect to y and the partial with respect to z. Just because I've constructed a function that I'd like to call a potential function that has its first derivative, partial with respect to x, equaling the x component of the forcing function, doesn't mean that f of x, y, z is going to satisfy the other two components. But if you look at the other two components, the partial with respect to y and z, and I'll underline them in red, their structures are identical. Their structures are identical. So if you were to integrate the middle component, the y component with respect to y, we would get the same function, capital F. And of course, if you did the same thing with the third component, integrated the partial, the third component with respect to z, we would construct the exact same potential function. Okay. Now, again, if you're worried about steps here, don't. I'm going to show you a step-by-step method for reconstructing potential functions very, very soon. Very, very soon. But right now, I've constructed a potential function. So that is, oops, I'm going to go back to black here. That is, there exists, all right, let's do it this way. I found a function f, not a vector field, but a function f, such that the vector field f is equal to the gradient of the small function, the scalar function, not a small function, the scalar function f. So Newton's law of gravitation, F is a conservative field. This is extremely important in physics. This is really, 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 really important in physics. Those of you who have studied the work energy theorem and conservation of energy, you know why. And for the rest of you, you're going to see why. It really holds together a lot of non-relativistic physics. It really holds a lot of physics together. Okay. So right now, we've shown that the gravitational field that we experience near the surface of the Earth, which is all we experience because we remain very close to the surface of the Earth through our whole lives, that vector field is in fact a conservative field. Okay. Now what we haven't done yet is we haven't addressed the title of the course yet. The title of the course is the Fundamental Theorem for Line Integrals. I don't like the title of the section because the fundamental theorem is the binding factor in this, or binding force, no pun intended, in this section. But the real thrust of this section is the consequences, or involves the consequences of having a conservative field. Okay, so now let's get to the title of the section. Let's talk about what we mean by the fundamental theorem for line integrals. So let's review first the fundamental theorem from Calc 1. Okay, a very special form of the fundamental theorem. So before we dig into the fundamental theorem for line integrals, let's recall the fundamental theorem from Calculus 1. Okay, in Calculus 1, very often we abbreviate that as the fundamental theorem of calculus from Calc 1. Okay, the fundamental theorem from Calc 1 can be written, or one part of it, remember it has two parts, one part of it can be written as the definite integral from a to b of, let's say, f prime of x equals an antiderivative of the function. Well, the antiderivative of the derivative, an antiderivative, is the function at b minus the function at a. And this says something that is extremely important, although we may not see it yet. We'll see it when we start looking at physical consequences of things. But check out what this is saying. If you have, let's say, f prime versus x, okay, f prime is let's say f prime is a continuous function between a and b, and you integrate it, that is, you find the area under f prime. At that area, remember, the integral of a non-negative function gives you the area underneath the curve. That integral, that area, doesn't depend on the behavior of the function between a and b. It just depends on the endpoints. The integral depends only on the antiderivative at the right-hand endpoint minus the antiderivative at the left-hand endpoint. This is extremely important. This is one of the main points in this section. The integral of f prime depends only on the endpoints. That's a major theme for the rest of this semester, actually. We're getting information about the function between a and b, or the derivative between a and b. We're getting information about f prime between a and b. That's the area underneath f prime. But that information can be obtained by just gathering information at the endpoints. That's a huge idea in the remainder of this course. We're getting information about the interior of a region, in this case the interval between A and B, the function in the interior of a region between A and B, by just looking at what's happening at the boundary points. That's wildly important. We're not going to go too deep into what's called the divergence theorem, but the divergence theorem, where we're going to end this course, is basically this idea on steroids. And think about it. How do we get information about what's going on in the center of our planet? Well, we observe information. We observe. The only information we have is that information that is available to us on the surface. Okay, so we get information about what's going on in the center of our planet. That is, is our center of our planet made of iron, and is it rotating? I guess the theoretical answers to those things are yes. I'm not a physicist, so I'm only looking at what I've seen explained to me by physicists. And yeah, well, we haven't been able to go to the center of the Earth. The radius of the Earth is about 4,000 miles, so we're never going to get down there. So we only get that information by looking at what's happening on the boundary of the Earth, the interior of the Earth. That is on the surface. That's what's going on here on a one-dimensional kind of scale. We get information about what's happening to f prime simply by looking at the endpoints. The integral depends only on the endpoints. I'm distilling it way down. Okay, if you're not with me, you will be very, very soon. So now to the fundamental theorem of calculus for line integrals. Okay, so let's start out with a curve in 3 space. Let's start out with a curve in 3 space. Let me draw that curve. I guess I'll use blue. Why not? Okay, so here's our curve in 3 space. Oops. Okay, and let's identify that curve. So let's identify the curve C. The curve C, and I'm going to use some terminology that's not going to be too important for us to get real rigorous about. I'm going to but I'll explain what I'm talking about. Let C be a smooth curve. R is given by some position function vector of time, t, for t between A and B. And essentially, smooth curves are curves that don't have any sharp edges. Okay. Even more precisely, smooth curves are curves that have a continuous tangent vector. Okay. Okay, so the tangent vector doesn't make any wild turns. If the tangent vector doesn't make any wild turns, then the curve won't have too sharp of edges, and we'll call it smooth. Okay, the smoothness can be made much more rigorous. So since this is a course in computational calculus, we're not going to be too concerned with the fine details of smooth curves. Okay, in any case, we have, let's say I'm going to draw the initial position and final position vectors for this curve. So I'll stay in black. Here's R of A. Here's my position vector at A. And I'll draw my position vector at B. So here's R of B. The fundamental theorem of calculus for line integrals is very similar to the fundamental theorem that we looked at just from Calc 1 a few minutes ago. Okay, so let's say some more preciseness. Suppose f of t is continuous for points along the curve C. Okay, don't obsess too much about that. Okay, these are the fine details that if you're a math major, you'll be returning to this again when you study analysis, or maybe in more specifically a specific course in multivariable calculus. Okay, so here's the result. Here's the fundamental theorem. Fundamental. I wonder if you can hear that ambulance going by. I could stop the video, but I'm not going to. Fundamental theorem for line integrals. Here goes my dog. Okay, it says something very similar to the fundamental theorem from calculus. It says the line integral along C, not of the derivative, but of the gradient of f dotted with dr. Okay, this line integral, the value of it only depends on the function at the two endpoints. The function evaluated at r of b minus the function evaluated at r of a. It's a direct extension, actually, of the fundamental theorem that we looked at. This is amazing. This is saying, without looking too much at a physical example, when we will real soon, we'll be looking at an important physical example. This is saying that this line integral depends only on the values of the function at the two endpoints. We gather information that is the line integral along the entire curve from r equals a to from t equals a to t equals b by just gathering information at the two endpoints. Okay, I want to show you a real brief proof of this. I'm not going to ask you to prove it on a test, but I want you to see how proofs of these results happen, and these proofs will occur even in computational math courses for the sciences when you start getting into third and fourth year math for physicists and stuff and engineers. Okay, so the proof. Okay, so I want to show that the integral of the gradient, basically the integral of gradient of f dot dr, only depends on the endpoint. So let's start with the left hand side. The integral of the gradient of f dot with dr. Okay, remember in our last video segment, how do we evaluate a line integral? Well, we parameterize the curve and we stuff the parameterization of the curve into the integral and turn it into an ordinary Riemann integral from Calc 1. Okay, well, we already have the curve parameterized. I'm saying that we're starting out with this smooth curve, r equals r of t. So let's stuff that into both the gradient and into dr. Let's see what we get. So this is not going to look really exciting on this next line. The gradient of f evaluated at r of t. Okay, and what's dr? dr is r prime of t dt. Okay, now let's write these quantities in component form. So this is the integral from a to b of, well, what's the gradient? It is the partial with respect to x of the function, the vector whose components are the partial with respect to x, the partial with respect to y, and the partial with respect to z, respectively, dotted with, and what's r prime? R prime, our old velocity vector. It's dx dt, the vector whose components are dx dt, dy dt, and dz dt. Okay, respectively. Integrate that with respect to time. Let's perform this dot product. This becomes the integral from a to b of the partial of f with respect to x times dx dt. Remember, the dot product is a scalar product, so it turns two vectors into a scalar. The net result is a scalar. So partial of f with respect to y, dy dt, plus the partial of f with respect to z, dz dt. Integrate that with respect to t. Now, here's the question for the ages. Do you recognize the quantity that we're integrating? It should look really familiar, really familiar. It looks like the chain rule. It looks like the chain rule. It looks like the chain rule for the derivative, ordinary derivative with respect to t of the function f. Now this function f was evaluated at r of t. Okay, remember r of t has an x component, a y component, a z component. So this is the function f along the curve. And the chain rule, this is what we get by the chain rule. So I'll write that in for you. By chain rule. Okay, now we're back in Calc 1. What's the derivative? Oh, sorry, the integral of the derivative. When you integrate the derivative, you get the function. This is the fundamental theorem in Calc 1 now. So this is the function f of r of t taken between a and b, and we get our result. The fundamental theorem of calculus from Calc 1 says this is the value of the function at r of b minus the value of the function at r of a. Okay, done. This is a proof of the fundamental theorem of calculus for line integrals. No, don't get too lost in the details of the proof. I mostly want you to understand what what the fundamental theorem is saying. It's saying when you integrate the gradient, of f dot dr, that integral only depends on the endpoints. When a line integral only depends on an integral, on the endpoints, that line integral is called path independent. Okay, so let me write that out again. We're talking about something that is going to follow us through the rest of the section. Path independence. Hence, the integral of the gradient of f dot dr does not depend on the path. This theorem says that that integral is path independent, is independent of path. Okay, so the integral of gradient of f dot dr along the curve C is path independent. Since its value, getting just too sloppy too soon, its value only depends on the endpoints of the path, and not the particular path to get between those two endpoints. Doesn't matter what the shape of the curve is, as long as it's a smooth curve. Doesn't matter what the shape of the curve is between t equals a and t equals b. That integral equals the same thing. Okay. So what does this mean in terms of computation? So computation, what does this mean? Or how do we compute these? The integral along the curve C of the gradient of f dot dr equals the value of the function at the endpoints r of b, let's say x2, y2, z2, minus the value of the function at the initial point, x1, x1, y1, z1, in R3. In R2, it would be x2, f of x2, y2, minus f of x1, y1. Okay, so this is in R3, and this is in R2. And this extends to higher dimensional spaces too. Okay, so this would also be true in space-time. Oh, I should be careful what I say. Yeah, this extends to higher dimensions. Okay. All right, now let's talk about the implications of this. What does all this mean physically? This is a very important concept of path independence. So let's talk about what the implications of all this are, or some of the implications are. Okay, so in general, when we move an object along a curve from one point to the next, from point A to point B, we get a different amount of work than if we move the same object along a different curve under the influence of the same force. Okay, so in general, if you haven't had physics, don't get too lost in this terminology. In general, we have the integral along, let's say, C1 of f dot dr, okay, is not equal to the line integral along a different curve of the same forcing function, or function f, which doesn't have to be force, but very often it is. So generally, this is saying that the work resulting from moving an object along a curve depends on the path. Okay, so let's write that out. The work generally resulting from moving an object along a curve between two the same endpoints. The moving along a curve along different curves depends on the path. Depends on the path. Okay, so what does that statement mean? It means that unless I have a very special force field that I'm located in, if I'm pushing a refrigerator from across my kitchen floor, from one end of the kitchen to the other end of the kitchen, I will do different amounts of work depending on the pathway that I push the refrigerator, along which I push the refrigerator or move the refrigerator. Okay, now this is where we start getting into the real important implications of all this stuff physically. But if my forcing function, my force field, or doesn't have to be force, let's just call it a force field, but if my force field F is equal to the gradient of some potential function, then what does that mean? That is, if the force field we can consider F is conservative, then the integral along C1 of f dot dr, that's the work required to move the object along C1 under the influence of f, is equal to, well, the force is conservative, so this is the work along C1, or the line integral along C1 of the gradient of f dot dr. That's what it means to be conservative. But the fundamental theorem of calculus for line integrals says that this is simply the value of the potential function at t equals b, so at r of b, minus the value of the potential function at t equals a, so minus r of a. Okay. However, this must equal the integral along C2 of the gradient of f dot dr. Why? Because the fundamental theorem of calculus says so. It's using the fundamental theorem of calculus in the reverse order. That the difference between r of f of b and r of f of a should equal the integral along C2. But the integral along C2 of the gradient, the function, the force function is conservative. So this is nothing more than the integral along C2 of f dot dr. Now look at the beginning and end results. The work along C1 is the line integral f dot dr along C1. That equals the work along C2. So the integral of a conservative vector field is independent of the path of integration. This is the bottom line here for this implications concept. Okay, so the integral of a conservative field which I'm considering as force, just so we can kind of intellectualize this. Specifically, the integral of a conservative field, the integral of a force field if you want, is independent, is path independent, is independent of the path of integration. Path of integration. Okay, so back to the refrigerator. So if the force that the force that my refrigerator is influenced by as I move the refrigerator from point A to point B is a conservative force, then I'm going to do the same amount of work whether I push the refrigerator straight across the floor or if I push it in a zigzag motion for 55 years, moving in different positions from position to position. And that's true. The gravitational force is a conservative force. So the work required to move an object under the influence of a conservative force field is independent of the path. It only depends on the starting point and the ending point. This is huge, 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 huge in physics, okay? And now, something we haven't done too much of is specific examples in the last half hour or so. So let's take a look at a specific example. Okay, so example. I think I'm going to write out the example off camera. Okay, here goes. Use the fundamental theorem of line integrals to find the work done by the force F equals 2xi plus 4yj. Okay, so we're in 2 space. To move an object from the point 1, 1 to the point 3, 5 along a straight line. Okay, now what we're looking at is the same force field that we basically started the lecture out with. This force field is conservative. Okay, I came up with the potential function. So we haven't talked about how we get the potential function yet, but I did construct one for you. Okay, we kind of are inching our way to how to do it. We basically integrate somehow. So F is conservative. Okay, we saw this since F equals the gradient of the scalar field small f for a potential function f of xy equals x squared plus 2y squared. 2y squared. Okay. Okay. Very soon we'll be looking at a very straightforward step-by-step method for finding a potential function. Okay. So since we can do that, since we found that we have a conservative force, the work does not depend on the path. The work is path independent. Path independent. Doesn't matter if I took it directly there along a straight line or if I twirled around for 1,000 years in different curves and ended up at B finally. The same amount of work would be done. Okay, so the work, which is defined as the integral along C, and we'll call C the line segment, the integral along C of f dot dr. Okay, but we don't have to evaluate this line integral directly because we have a conservative field. So it's the integral along C of the gradient of f dot dr. Okay, but the fundamental theorem of calculus for line integrals says that this is nothing more than the potential function at B minus the potential function at A. Well, I think B was 3, 5, you know, and A is 1, 1. Okay, well, the potential function is x squared plus 2y squared. So 3 squared plus 2, 5 squared, that's the function at 3, 5, minus 1 squared plus 2 times 1 squared. And this is 56. Don't stress units right now. Okay, so I haven't expressed the units of our force, so let's just say 56 units of work for right now. Okay, all right, so we could have completely ignored the fact that we have a conservative field here. It's not a good idea, and I want to take some time to say that. We could have evaluated this line integral directly, ignoring the fact that we have a conservative field. You don't want to do that. A couple of things can happen if you ignore the conservative nature of the force field and try to evaluate the integral directly. Basically, the line integral could be very difficult, if not impossible, to evaluate directly. I stated that it's a linear line, a linear path. What if I just said the work along an arbitrary curve? If you're not with me, let's ignore the fact that we have a conservative force and see what would be involved here. Okay, so let's do that now. Ignoring that the force is conservative may come with a huge cost. The worst case scenario is that it would be impossible for you to evaluate the line integral directly. Okay, for our case, the cost isn't so bad. Let's see, this is good practice. Let's evaluate this work integral directly. Okay, so let me copy our picture from above and I'll come right back. Okay, so here's our picture again. Suppose we're going to compute the work directly. Well, the first thing we need to do is to parameterize the curve. Well, this curve is not so difficult to parameterize. One, because we're told what the curve is, okay, which isn't always the case. Sometimes we just want to know the work between two endpoints along an arbitrary curve. And two, it's even simpler than that. It's a line segment. So remember, we talked about this in an earlier segment, earlier video segment. A line segment from way earlier in our course, segment, I can spell segment here, as a line segment, is R equals the initial position vector plus R1 minus the final position vector minus initial position vector t for t between 0 and 1. This is always parameterize a line segment for t between 0 and 1. Okay, so for our case, r equals, well, the initial point is 1, 1, so I can view that as giving me the initial position vector, plus r1 minus r naught, r0. Well, the point B is 3, 5, the point A is 1, 1. So R1 minus R naught is a displacement vector from A to B, and that's 3 minus 1, subtracting the first components, 2, and 5 minus 1, 4, T. Okay, where was my phone? Hang on a second, I'll be right back. Sorry about that. Yes, I still have a landline. But you don't get to know it. All right. Most people who know it are telemarketers anyway. All right. Okay. So here's our the vector function defining our line segment. So how do we evaluate a line integral? We stuff the parameterization of the curve into the integral and turn it into a regular ordinary Riemann integral from Calc 1. Okay. So the parameterization is x equals 1 plus 2t, and y equals 1 plus 4t for t ranging between 0 and 1. Our work then, again, this is ignoring the fact that we have a conservative field. The work is the integral along the curve C of f dot dr. Okay. Well, the force function was I already forgot. 2x and 4y. Okay, so components are 2x and 4y. So 2x, 4y. Okay, so how do we evaluate a line integral? We stuff the parameterization into the forcing function. So this is going to be the vector whose components are 2 times 1 plus 2t, 2x, and 4y, 4 times the parameterization for y. Okay, and dot dr. Well, what is dr? It's 2, 4 dt. Okay, so how did I get that? Dr is the vector whose components are dx and dy. Okay. Or you can think about it as r prime dt. Okay, so r prime would be, rather dx would be 2, dy would be 4. So we get 2, 4 dt. dx and dy would be 2 and 4 dt respectively. Okay, so then this is carried between 0 and 1. Look at this cost. Look at the cost of ignoring the fact that we have a conservative vector field. I'd have to evaluate this integral. It's not that tough of an integral, primarily because the force function is not that tough, and the path is super simple. But I still have to evaluate this. First I evaluate the dot product, so this becomes, I'm taking the dot product, 4 times 1 plus 2t, multiplying the x components together, plus 16 times 1 plus 4t. And I think I've made my point. We can distribute and combine like terms, but this equals, after about 3 to 5 more minutes of integration, this equals 56. So the cost here was minimal. The cost here was minimal because the force function was very, very simple, and the path was simple. But again, and I know I'm repeating myself, but this has been a problem on exams. This could have been a much more difficult situation where evaluating or finding the work would be relatively simple if you note that we have a conservative field and then use the fundamental theorem of calculus for line integrals, just looking at the endpoints. Or it could be impossible at worst, or very, very difficult at best if the path of integration is difficult or unknown or not specified. Okay. So I want to summarize this important concept that relates conservative forces or conservative vector fields more generally with path independence, and I want to mention one more important theorem specifically related to line integrals along closed curves. Okay, so let's do that. So here's the first of the two big theorems, which we've been concentrating on. Now I wrote some things in red here. These are fine details that, again, if you're not a math major, you don't have to concern even if you are a math major taking this course, you don't have to concern yourselves with too much or at all in this course. This course is a course in computational calculus. We're not concerned with the rigorous proofs of these results. We want you to become familiar with these tools of the sciences so you can use them. So suppose we start with a vector field that's continuous. We don't worry too much about the continuity. The force fields or the fields that we're going to be using are continuous. On an open, and there's a word we haven't looked at, an open set is very similar to the concept of an open interval. The boundary is not included. So boundary not included. So suppose that we have a continuous function on the interior of a set, a region. Okay, and there's another term, connected. Connected essentially means the region in 3 space or 2 spaces, one piece. We're not looking at regions that are made up of 2 or more separate pieces. So that's roughly what we're talking about here by a connected region. Okay, and our regions will be both open. We can consider the continuity on open, and our regions will be connected. So don't worry about that. The big thing is that we have f is conservative if and only if the line integral is path independent. We talked about one way of this theorem. This theorem goes 2 ways. It says if f is conservative, then the integral is path independent. But it works both ways. If the integral is path independent, then you also have the force is conservative. So if you wanted to show that your force was conservative, you could start by determining that your work integral is path independent. I don't recommend it. That's a huge undertaking. In any case, this is just summarizing and extending a little bit what we just talked about. The important thing for us is if our force field or field is conservative, then the amount of work required to move the object from one point to the next doesn't matter. Is independent of the path. It doesn't matter what the path is. Okay. So here's our second important theorem here. Let's see if you can help me come up with the conclusion to this theorem. So I only wrote 1/2 of the second theorem. The big theorem about closed curves. Okay, so now assume that we're looking at C being a closed curve. Okay, so the integral along C, along this closed curve, a circle or any curve that's closed with smooth edges here. Okay, is path independent. If and only if what? Now, imagine that you have an integral that's path independent. That means the integral is going to, if you have the integral along a curve is path independent. That means the integral along the curve is only going to depend on the starting point and the ending point. Okay? So if the starting point and the ending point are the same point, what happens when you subtract those values, those potential values? Okay, so what do you think? So the integral is path independent in D if and only if the integral along C of f dot dr equals what? 0 along any closed path C inside of our region that we're considering. Okay, I want to give you a really simple proof of one direction of this theorem. Remember this theorem, when you have something that says A if and only if B, it means if A then B. It also means if B then A. So if I say I'm going to order a hamburger if and only if I get an order of fries, that means if I order a hamburger, then I'm going to get some fries. It also means if I get some fries, I'm going to get a hamburger. Okay. Okay. So let's take a look at a proof one way, simple proof one way. You're not responsible for this proof. I think it would be instructive. It really kind of helps us pull all this line integral stuff together. Okay. So I want to assume that the integral is path independent. So let's assume the first thing. Assume that the integral along curve C of f dot dr is path independent. Path independent. Okay. So I want to prove a specific result about closed paths. So let's let C be a closed path. We're restricting ourselves in some region of 3 space or 2 space, so in D. Okay, so here's our closed path. I'm going to draw a picture of it. Okay, so I want to divide up C. I'm gonna take 2 points on this path. One point I'm going to call this closed path. I'm going to call that point A. I'm going to call this point B. And here's the orientation of our path. Let's say it's, remember paths have orientations as well. So it's in some sense counterclockwise, okay? So let's break up C. Let's write C as the union of 2 curves, C1 and C2, the sum of 2 curves, if you will, where C1 goes from A to B and C2 comes back. Okay. So since the integral along C of f dot dr is path independent, the integral along C1 of f dot dr is not the integral along C2, right? C2 is going in the wrong direction. C2 is going from B to A, so it's equal to the integral along the opposite of C2. Remember, the integral along the opposite of curve just moves along the curve in the opposite direction. Okay, so C1, the curve C1 and the curve opposite C2 are both going from A to B. So the integral's path independent, so the integral along each of those curves should be the same. So now let's show the integral along the entire curve C is 0. So that's the integral along C of f dot dr equals, well, the integral along C is now the integral along C1 union C2 of f dot dr. And we discussed the definition of the integral along different portions of a curve. It's the integral along the first portion, f dot dr, plus the integral along the second portion, f dot dr. Okay, we're getting there. However, what is the integral along C2? What is the integral along C2? We also have a theorem that allows us to deal with reversing the order of the orientation of a curve. It's equal to the opposite of the integral in the opposite direction along C2, f dot dr. Okay, well, what's the integral along the opposite direction of C2? That's the integral along C1. This is 0. Okay, it's pretty nifty. Okay, the important thing is that there's a connection between path independence and integrals along closed curves being 0. If you have a path independent integral, if the work doesn't depend on the path to go from one point to the other point, then you're not going to do any work along any closed curve. So that says that if I push the refrigerator from one end of my kitchen to the other end of the kitchen and then push it back, since the force due to gravity is conservative, then I'm not going to do any work. Okay, so it's not generally true that if you end up in the same place that you do no work. But if you're working under a conservative force field, that will be true. Okay. Now we still got some work to do. We're making our way toward the end of this section, but we have some work to do. Before we do that, I'd like to give you a summary, a very nice summary, I think. And I didn't come up with this summary. This summary came out of a textbook that I studied from when I was your age. This years ago. Your author doesn't give you this. This summary gives us all a sort of equivalent relationship, a set of equivalent relationships between conservative forces, gradients, path independence, and integrals along closed curves. So let me get that off camera for you. So here it is. The following are equivalent. which means if you have any one, you have any of the others. First, if you have the first, and you have the fourth. If you have the third, then it applies the second, etc., etc., etc. So if the vector field force, if you want, is conservative, then there's a scalar function such that the force is equal to the gradient of a scalar, which is absolutely equivalent to being the force field being path independent. I forgot a T at the end of independent. I should put that in black. And that's absolutely equivalent to the integral along every closed curve in our area, our domain D, is 0. So if every integral is 0, then you have a conservative force. If you have a conservative force, then the work is path independent. If the work is path independent, then the work is 0. So each of these is equivalent to the other. So if you have one, you have the other. Okay. So physically, and I guess I've been saying this all along, but I'm going to concentrate on it. Physically, the work done in a conservative force field is two things. The work done in a conservative force field is independent of path. And also, if that path is closed, the work done is 0. There will be no work done in a along a closed curve if our force is conservative, if our vector field is conservative. So what we're missing here is this. You see, the idea is to be able to find this potential function so we can avoid evaluating a line integral. So before we do that, we want to know that we have a potential function to look for. That is, we'd like to know, or we'd like a test for determining whether we have a conservative vector field. Okay, so how do we determine if our force field, or our field more generally, is conservative? Well, using the summary is too hard. I could brute force try to find the scalar potential function. I could determine that the integral along every closed curve is 0, or I could show that my integral is path independent. That's too hard. I want a concise test for determining whether I have a conservative force field or a conservative field. Okay. So I'm gonna motivate it. I'm gonna give you an idea of why the test should work, and then I'll state the test itself. Suppose that F is conservative. What does that mean? That means, so arrow, let's just make the arrow a little better. Then, we'll do it that way. F is equal to the gradient of some potential function. So is the gradient of small f for some potential function f. And the function could be f of x, y, z, or f of x, y. Let's restrict ourselves right now to R2. Okay, so suppose f is conservative in R2. There is a corresponding test for R3. It's a little more complicated. We'll see it in, I think, toward the end of our semester. Let's suppose we're in R2. Okay, suppose we have a conservative force, then that means there exists a potential function. So that means that f equals the gradient of some scalar field. Okay, so that is f equals the gradient of some scalar field. Okay, now let's go back above, and let's identify what f looks like. Let's say f equals some p of x, y, I plus q of x, y, j. Okay, and I realize I'm mixing notations here. It might be a little confusing. It's no big deal here. Okay, so f x I plus, I'm just changing to be consistent with my I and j notation, standard basis vector notation. So what does that mean? So if f is equal to the gradient of some potential function, that means that the partial of f with respect to x needs to equal p, the first component of my forcing function, and the partial with respect to y should equal q. Okay. So now let's take more derivatives of these two equations. Let's take the derivative with respect to y of the first one. So this has the second partial of f first with respect to x, and then with respect to y is partial p partial y. Okay, now let's take the second equation and take the derivative of it, find its second partial, take a derivative with respect to x of it. So equals partial q partial x. What do we know about mixed partial derivatives for our course? They're equal. This is the test. So partial p with respect to y equals the partial of q with respect to x. If you take the first component of your force, the p, and you take its derivative with respect to y, and you get the same thing if you take the second component of your force and take its derivative with respect to x, that's the test. Now, I proved this one way. I've showed that if we have a potential function, then this equation must be satisfied. But the test works both ways. We won't prove the other direction. Okay, and you're not responsible for the proofs. So here's the test. The test for a conservative f equals p of x y I plus q of x y j. Test is the partial of p with respect to y equals the partial of q with respect to x. So the function is conservative if and only if this equation holds true. Okay? F is conservative. If and only if the partial of p with respect to y equals the partial of q with respect to x. Okay? Let's use that in our next example. Okay, so here's our first part of this example. Show that the function f equals the vector whose components are 2xy for I and x squared plus y for j is conservative. Okay, so we're going to use our test for a conservative function, vector field. So p equals 2xy, q equals x squared plus y. So let's find the partial derivative of p with respect to y. And that's 2x. And what's the partial of q with respect to x? It's 2x. Okay, so since the partial of p with respect to y equals the partial of q with respect to x, f is conservative. Okay, so next let's find a potential function. This is something new for us here. Let's find the potential function. Okay, so find a potential function. So that means there exists a function, a scalar function, f of xy, such that f equals the gradient of f, of small f. Well, f, that's my original forcing function, if you will, 2xy I plus x squared plus yj. And since I have a conservative field, that must equal the partial derivative of the scalar function, a potential function with respect to xi plus the partial of that same function with respect to yj. So set the component functions, the components of these two sides equal to each other. So that says that the partial of f, my potential function with respect to x, equals the x component of my forcing function, and the partial of f with respect to y equals a y component. And we're going to use both of these partial derivatives to reconstruct the potential function. So what I'm going to do is I'm going to take the first partial, the one with respect to x, and I'm going to integrate both sides with respect to x. Now remember, when you integrate with respect to x, you have a constant of integration. We get something a little more here, though. I'm going to integrate with respect to x. So f equals the integral of the derivative with respect to x, and I'm going to integrate it with respect to x. Now, when I differentiated to get that partial, I held y constant. So when I integrate with respect to x, I'm doing the same thing. I'm going to hold, this is very important, y constant. So when I add a constant of integration, anything with y in it will also be constant. So my constant of integration isn't really constant. It's any function of y. I'll repeat this in a second. This is really important here. It's also not very difficult. You'll understand this. When I integrate with respect to x, then that means I'm holding y constant, which means I'm holding anything that has a y, any function of y is constant. So if I add a quote-unquote constant of integration, anything with respect to y will be that constant of integration. If you're not sure, take this function that I've reconstructed and take the derivative back again with respect to x. Okay, do that in a second. Let's proceed, and I'll show you what I just said, or repeat what I just said. If I integrate 2xy with respect to x, I'm going to get x squared y. Integral of x, 2x is x squared, but y is held constant, plus that mysterious h of y. Now take this function, just to show that I haven't done anything magical here by putting h of y instead of a constant of integration. Take the derivative of both sides with respect to x. What's the derivative of x squared y with respect to x? It's 2xy, which it should be. What's the derivative with respect to x of any function of y? It's 0. So when you integrate with respect to x, any function of y will be that constant of integration. Okay. If you integrate with respect to y, then any function of x would be constant. Okay. So now what I'm going to do is I'm going to use something that I haven't used yet. I haven't used the fact that I also have the partial of f with respect to y. So now I'm going to take the function I just found, and I'm going to take a partial derivative, not with respect to x, but with respect to y now. Okay, so what's the derivative of x squared y with respect to y? What's the derivative of y with respect to y? It's just 1. What's the derivative of h of y with respect to y? It's just an ordinary derivative, h prime of y. What must that be equal to? It must equal the thing that I haven't used yet. It must equal the partial derivative of f with respect to y provided by the second equation. Okay, so now solve that resulting equation for h prime of y. Subtract x squared from both sides. H prime of y should be y. I want h of y, so integrate both sides with respect to y. So h of y should equal y squared over 2, or 1/2 y squared, plus a what? Plus a regular old constant c. So my potential function then looks like x squared y plus that h of y, which is 1/2 y squared plus a c. I only need one potential function. So let c equal 0. Since I'm only looking for one potential function, choose the easiest one possible. Let c equal 0. function, let c equal 0. You could let it equal pi over 17 if you want, but let's make life a little simple as possible for us. X squared y plus 1/2 y squared. So that's a perfectly good potential function. Okay, last part of this example. So let's evaluate the integral of f dot dr, where c is any smooth curve from -1, 1 to 0, 4. Okay. Okay, now let's make sure we understand. So let's make sure we understand what's going on here. I want to find the amount of work required to go from -1, 1 to 0, 4, where I haven't specified the curve. So I can start at -1, 1. I can think of a lot of very bizarre curves that will go from -1, 1 to 0, 4. I kind of put a corner point in that one, so it's not really smooth. So technically I should do that here. There. Okay. It's impossible for me to parameterize all of them. So let's use the fact that we have a conservative field here. So the integral of f dot dr is path independent, since we have a conservative function, a conservative vector field. Okay, the fundamental theorem of calculus for line integral says that this is nothing more than the integral is nothing more than the line integral of the gradient of f dot dr. Okay, and that's equal to the value of the potential function. This is the fundamental theorem. The value of the potential function at the end point minus the value of the potential function at the beginning point. Okay, well, the potential function is x squared y plus 1/2 y squared, right above. X squared y plus 1/2 y squared. 0 squared times 4 plus 1/2 times 4 squared. That's x squared y plus 1/2 y squared. Minus at -1, 1, it's -1 squared 1 times 1 plus 1/2 times 1 squared. And you can trust me on this if you want, or you can compute it on your own. It's not 12, it's 13 over 2, 6.5. Okay, so be careful on your homework and on your exam that you don't discard the possibility or neglect the possibility that we could have a conservative field when you're evaluating line integrals or work integrals. Okay, it could save. At least it could save you time. At best, it could save you from losing all the points where it's impossible to parameterize the curve or to evaluate a very complicated line integral directly. Okay, so we're finished with the lecture materials for this section. I wanted to end the section with two outrageously important results from physics. If you haven't had physics, don't worry about it. Don't worry about it at all. But if you haven't had physics, you're very likely to take it very soon because you're most likely a science major. And these results are, like I mentioned, huge in physics. So let's take a look at a couple of really important physical situations. Okay. Okay, so we need a couple of preliminaries for this last example. These are items from our past here. So I'm gonna highlight them, saying blue. It'll work. Okay. The first is that the derivative of, if v is a function of time, vector function of time, then the time derivative of v dot v is 2 times v prime dot v. Okay, this one's real easy to see. If you use the product rule, you get the derivative of the first dot the second plus the first dot derivative of the second, and those two things are the same. v prime dot v and v dot v prime are equal, so you get 2 v prime dot v. The second is from really early in the course, that when you take a dot product of a vector with itself, you get the length of the vector squared. Okay, so we need those two things, and we'll need them in about 30 seconds to a minute. So work energy theorem. This is one of the two big results that we want to end with. This is from physics. It's also in your textbook. So given a curve C, I drew a little curve C for you there, for time between A and B, and let's also be given that we're moving an object. If we couldn't put a refrigerator at R of A, and we're pushing a refrigerator along this weird curve in 3 space until it hits R of B. So we move an object along a curve C under the influence of some force F of x, y. Okay, gravitational force or whatever, just some force X, depending on X, depending on X, Y, and Z, actually. That's really kind of important here. Okay, because we're in 3 space. This goes for 3 space. Also think it generalizes. So I want to compute the work. So let's do it. Let's compute the work required to move the object, refrigerator, or whatever you want to move along the curve C. It's the line integral of f dot dr. Okay, how do we evaluate line integrals? We parameterize the curve and stuff the curve into the integral. So we take the force and we evaluate it along the curve. And we dot that with dr. And dr is nothing but r prime of t, if you will. Let's put the of t's in for now. dt and time range. This is regular integral now, a Riemann integral from a to b. Okay. Now for this next step, I'm going to use Newton's second law. Newton's. I could have put that in the preliminary. Second law. I'll just use it without stating it as a preliminary. This is Newton's second law says that the sum of the forces acting on an object equals the mass times the acceleration of the object. So the force is equal to the mass of the object, let's say m, times acceleration of the object. Okay, and r prime of t, so that's what the force equals. That's Newton's second law. And r prime, that's the acceleration. I'm sorry, that's not the acceleration, that's velocity. So this is dotted with v of t dt. Okay, so Newton's second law was used right there. Alrighty. So acceleration is nothing more than the time derivative of velocity. So acceleration is v prime. Okay, I'm going to remove the of t's. So this is just v prime dot v dt. Okay, now one of my preliminaries says that reading on the right hand side, 2v prime dot v is the derivative of v dot v. So I could use that in the form v prime dot v, divide both sides by 2, equals 1/2 the derivative of v dot v. Okay. Okay, so v prime dot v is the same thing as 1/2 times the time derivative of v dot v. Integrate with respect to time. Now m times 1/2 is a constant, so I'm going to bring 1/2 m out. And v dot v is the length of v squared. Length of the v velocity vector squared dt. Now, what do these two operations essentially do? What does the fundamental theorem of calculus say happens with the integral and the derivative? They cancel each other out. Okay, so this is 1/2 m times the length of v, I'll put the of t back in, squared, from a to b. And here, next step is our amazing result. It's absolutely amazing. Put in the upper and lower limits of integration. This is 1/2 m times the magnitude of V of B squared. Those of you who had physics, what are these quantities? Minus 1/2 m magnitude of V at A squared. Physics types, what's 1/2 mv squared? That's kinetic energy. Okay, this is the kinetic energy at B minus the kinetic energy at A. Okay, where K means kinetic energy. If you haven't had physics, don't worry about it. You'll be seeing this stuff soon enough when you take physics. Unless you're a computer science major or something, you don't have to take this. And hopefully it's just interesting. This is the work energy theorem. It says that the amount of work done to move an object along a curve is nothing more than the change of the change in kinetic energy between the 2 points. Work, energy, work related to energy. Now, I want to end this section with another powerful result. Now we're still moving the object along this curve. Now let's make the assumption that the further assumption that the force function is conservative. Now assume that F is conservative. And you'll see the connection between my use of the word conservative and something from physics, which he also uses the word conservative. You physics types, what am I heading for? I'm going to use this work energy theorem, and I'm going to plop in the idea that my force is now conservative. What happens? What happens if you physics people? Okay, just think about it. If you don't get it, it's okay. Okay, in physics, this the potential function that we talk about is not quite potential energy. In physics, P of x, y, z equals the opposite of that potential function that I found is called the potential energy. Potential energy of the object that when I'm moving the refrigerator or whatever, the object at x, y, z. Okay, so the potential that we found is not quite the potential energy in physics. So since the function or the vector field the force field is conservative, F equals the gradient of small f, or in terms of the potential energy function, F equals the negative of the gradient of the potential energy function. Okay. So now let's look at work again. Work is the integral along C of f dot dr, but the function f, the vector field f is now conservative. So f equals the negative of the gradient of my potential energy function dot dr. That negative can come outside. Gradient of potential energy function dot dr. Now use the fundamental theorem of calculus for line integrals. This is negative. What does the potential energy? What does the fundamental theorem for line integral say? If you're integrating the gradient dot dr, then you just get the potential energy at the end point, the later point, the final point, minus the potential energy at the initial point. Let's combine this with the last results. Combining with previous results. Previous result about work, the work energy theorem. Well, work equals the negative P of B minus P of A, which is the same thing as P of A minus P of B. That's what work equals. But what does the work energy theorem say work equals? It equals the kinetic energy of B. minus the kinetic energy of A. We're almost there, folks. We're going to end this with a powerful, powerful statement that a lot of you already know, but I just proved it for you here. Okay, so now let's get the potential and kinetic energies at A on one side, potential and kinetic energies at B on the other side. So this is saying that the potential energy at A plus the kinetic energy at A equals the potential energy at B plus the kinetic energy at B. There's no change in the sum of the energies. The sum of the potential and kinetic energies at A equal the potential and kinetic energies at B. There's no gain or loss of energy. What do we have? This is called conservation of energy theorem. It doesn't work for every force. It says that the sum of kinetic and potential energies remains constant. Sum of kinetic and potential energies remain constant under influence of what kind of force? Of conservative forces. I'll be more specific. Of a conservative force. If your force is conservative, you will have conservation of energy. Okay, that was a long section, but the section is at the end. So go ahead and start homework on this section as soon as you can, and I'm looking forward to talking with you all again very, very soon.